Continuing to study approximation results in continued fractions, now we're going to look at best approximations of the first kind, for which we're going to introduce a notion called semi-convergence. So let's just remember a few things. If x is an irrational number, then p over q is said to be a best approximation of the first kind to x if the distance from x to p over q is smaller than the distance from x to a over b for any rational number a over b, where b is less than or equal to q and you didn't actually just pick p over q to begin with. In other words, of all the rational numbers whose denominator is up to and including q, the closest one to x is p over q. That's what it means to be a best approximation of the first kind. If furthermore, multiplication by the respective denominators on each side preserves the same inequality, that's called being a best approximation of the second kind. In other words, of all of the multiples of x through qx, p is the integer closest to any of them. So what we have shown in the previous video is that convergents of x are exactly the best approximations of the second kind, with this possible exception of the first one. Now we can begin investigating, however, the best approximations of the first kind. So what we have shown, just to remember, best approximations of the second kind are also best approximations of the first kind. It is a stronger condition to be a best approximation of the second kind, and convergence of continued fractions very neatly solve that stronger problem. But if we were interested in the weaker problem of best approximations of the first kind, we'll see that convergence, while they are best approximations of the first kind, they're not the only ones. Okay, so let's define an operation. Suppose you have a over b and c over d, which are rational numbers in standard form, meaning that the numerator and denominator are relatively prime. Also, the denominators are positive. The mediant of the two numbers is a plus c over b plus d, reduced possibly if necessary. In other words, you're kind of adding them as if you were doing it wrong. If you just hand someone who's never added fractions and say, what's a over b plus c over d, they might just say a plus c over b plus d, which is not the actual sum of the two rational numbers, but now we're defining that to be the mediant. So here's a theorem. Suppose you have two rational numbers, a over b and c over d, and we're going to say that a over b is less than c over d. Then the mediant is in between them. So the original assumption that a over b was less than c over d, if we multiply by the positive denominators, we get ad is less than bc. So we can get both of these inequalities here. In the first one, we would cancel out this ab with this ab, and we would just have ad is less than bc, which is true. And here we would cancel out the d times c and c times d, getting the same a times d is less than b times c. But from these inequalities, you would exactly get a over b is less than a plus c over b plus d. Multiplying by the denominator would give you this. And similarly, the second inequality gives you that there. Okay, suppose you have a continued fraction with the partial quotients. We've got an irrational number, so it never stops. And we denote the convergence Pn over Qn. This is all totally standard. Recall that we have these recursive formulas. Pn plus 1 is an plus 1 Pn plus Pn minus 1, and Qn plus 1 is an plus 1 Qn plus Qn minus 1. Then for any choice of n, and now we're going to pick an I, which goes from 1 up to but not including the partial quotient an plus 1. We define the semi-convergence of x to be I times Pn plus Pn minus 1 over I times Qn plus Qn minus 1. So in other words, it's as if we were sort of computing Pn plus 1, but we're using a number here somewhere in between 1 and just before this partial quotient an plus 1. And similarly, we're computing something that looks kind of like Qn plus 1, but instead of putting the partial quotient here, we put something smaller. Okay, so begin with two rational numbers, p naught over q naught, which is a naught over 1, and p1 over q1, which is a naught a1 plus 1 over a1. If you take the mediant between these over and over again, you'll be constructing semi-convergence. And when I say take the mediant, so first, if we take the mediant between these two numbers, p naught over q naught, p1 over q1, you'll get p1 plus p naught over q1 plus q naught. Then take the mediant with p1 over q1 again. We're always going to take the mediant with the convergent with larger index. So we take the mediant with p1 over q1 again, and you'll get this. Take the mediant with p1 over q1 again, and you'll add a p1 up here, and you'll add a q1 down here, and so on and so on. And if you do this a total of a2 times, you will have exactly constructed p2 over q2. So all of these mediants are in between the previous one and p1 over q1. Okay, so they are increasing towards P1 over Q1. We're starting with P naught over Q naught, which is less than X. P1 over Q1 is bigger. The mediant is in between them. Then the mediant is in between this and P1 over Q1, so it gets a little bit bigger. The next mediant is in between these two, so it gets a little bit bigger, and so forth, until you manage to construct the next actual convergent, P2 over Q2. Then what you do, now that we have P2 over Q2 constructed, take the mediant of P1 over Q1 with P2 over Q2, then take the mediant of that with P2 over Q2, then take the mediant of that with P2 over Q2 over and over again, until you've added a total of A3 P2s in the numerator and A3 Q2s in the denominator. That will construct P3 over Q3. And now you will be decreasing towards P3 over Q3. So what we know from a previous video is that the convergence Pn over Qn converge to X. Each one gets closer than the last one. The even index terms are increasing towards X and the odd index terms are decreasing towards X. Mediants give us a slower way to do the same thing. It just takes more steps, but you're accomplishing essentially the same idea of approaching X from one side and the other. So here's a theorem. Suppose you take K, which is less than or equal to the partial quotient an plus 1, construct this mediant looking thing. It is on the same side of X as this term Pn minus 1 over Qn minus 1. In other words, as you take these mediants up to the partial quotient an plus 1, you stay on the same side of X as the lower index convergent that you're using to build this mediant. Once, however, you let K be larger than this partial quotient, you will flop over to the other side of X and you'll be on the same side of X as the larger index convergent Pn over Qn. So the partial quotient an plus 1, if you keep constructing these mediant looking things, is exactly where you flop from being on one side of X to the other. So we know that as we keep taking successive mediants between, observe this is going to be K Pn over Pn minus 1, KQn over Qn minus 1, this one right here. And this right here is just Pn over Qn. So continuing to take mediants with the Pn over Qn is how we keep adding 1 to this index K up here. The next value we take is always between the two we started with. So depending on whether n is even or odd, we're either increasing or decreasing, but towards Pn over Qn. So let's suppose, for example, n is odd. So Pn minus 1 over Qn minus 1 is an even indexed convergent. It is less than X. Pn over Qn is an odd indexed convergent. It is larger than X. As we keep computing mediants, we're between Pn minus 1 over Qn minus 1 and Pn over Qn. So we increase a bit compared to Pn minus 1 over Qn minus 1. Then we're in between that and Pn over Qn. We increase a bit more and so forth. If n were even, by the way, the picture would be reversed. As we've done several times, we don't reprove this for the even and odd case. They look essentially the same, but all of your inequalities get reversed. Okay, so now we know that Pn plus 1 over Qn plus 1 is less than X. Okay, so since n was assumed to be odd, this was an odd indexed convergent, it's larger. This was an even indexed convergent, it's lesser than X. But this will also be an even indexed convergent, so it's still less than X. So our mediants were increasing until they hit this, but we were increasing towards something less than X. They were all less than X. All right, so we're trying to prove this claim that as you construct mediants, Kpn plus Pn minus 1 over Kqn plus Qn minus 1, up to and including K being the next partial quotient an plus 1, this mediant looking thing is on the same side of X as this lower index convergent Pn minus 1 over Qn minus 1. But what we want to show is that as soon as you be larger than that partial quotient, it will be on the same side as Pn over Qn. And we've already established the first half. When K is up to and including an plus 1, we are still on the same side of X as the lower index Pn minus 1 over Qn minus 1. The second claim will follow if we just establish, again, we're just going to keep assuming n is odd, that if I were to pick this value, 1 larger than an plus 1, observe that if I need to compute this number, up to this point we would get Pn over Qn, and then you would get an plus 1, Pn plus Pn minus 1 over an plus 1, qn plus qn minus 1. You'd exactly be computing this mediant for the first term larger than an plus 1. If we can establish that that is bigger than x, well, if I keep increasing this, I only increase towards Pn over Qn, which was bigger than x because n was odd. So all we need to do is show that this one is bigger than x, and then all the rest will be as well. And again, if we want to do the case where n is even, it just reverses all the inequalities. We're not going to bother. Okay, we do happen to know, however, that since we've assumed that n is odd, Pn plus 2 over Qn plus 2 is still an odd indexed convergent, and those are all bigger than x. So we want to show that x is less than this number. We already know that x is less than this number. So if we can show that this convergent is less than or equal to this mediant looking thing, then since x is definitely less than this, it will be less than that as well. Okay, so what we want to show is that Pn plus 2 over Qn plus 2 is less than or equal to this number right here. And as already discussed, if we terminated the computation at this index, we'd have Pn over Qn. Then we add in one more partial quotient, we'll get an plus 1 plus 1, Pn plus Pn minus 1 over the same looking thing down in the denominator. So this is the inequality we want to establish to complete our proof. Okay, so we just need to establish this inequality here, but in the numerator, observe that what we have is an plus 1 Pn plus Pn minus 1, that's Pn plus 1 with an extra copy of Pn thrown in. And similarly in the denominator, if you distribute this and collect the an plus 1 Qn plus Qn minus 1, you'll get a Qn plus 1 with an extra Qn. Okay, so multiply the denominators, which are positive, so we don't need to flip about inequalities. That changes this into here is what we need to establish. If you distribute this all out, a few terms cancel, and in fact, this is all you need to establish. And now what we can do is we can collect some terms together, and we can move everything with an plus 2 on the left and everything without it on the right. But now look at those terms inside the parentheses by an plus 2 and on the other side of the less than or equal sign, it's the same thing. Now, we've already established that this balancing of consecutive p's against q's is always a power of minus 1. We've been working on the assumption that n was odd, so that makes it -1. So if I cancel out this -1, it flips the inequality. In other words, all we need to prove is that an plus 2 is bigger than or equal to 1, but that's certainly true. All of the partial quotients are positive integers, except perhaps a0, which is an integer, but we're looking deep inside the continued fraction expansion here. And all of these steps were reversible, so you can just start from the assumption that an plus 2 is bigger than or equal to 1 and work your way back to what we needed. So constructing the medians up to and including the next partial quotient will be on the same side as the lower index Pn minus 1 over Qn minus 1, but if you tried to use a k which was past the partial quotient, you would flip to the other side of x. So let's demonstrate this notion. We're going to take medians with Pn over Qn as we approach x from the side of the previous one, Pn minus 1 over Qn minus 1. The partial quotient an plus 1 is exactly how many times you can do that before you would cross the value of x. So let's suppose for the sake of argument that a2 is 4 and a3 is 3. So here's the real number line with x on it. P0 over Q0 will be less than x, and P1 over Q1 will be bigger than x, but closer than P0 over Q0 was. So let's take a mediant of P0 over Q0 with P1 over Q1. It will be in between the two, but because we have not reached the next partial quotient of 4 times, we're still on the same side of x as the lower index P0 over Q0. Do it again, do it again, do it again. But if we were to attempt one more mediant with P1 over Q1, we'd be doing it more times than the next partial quotient A2, which was 4, so we would cross to the other side of x. So we don't do that, and observe that 4P1 plus P0 over 4Q1 plus Q0 is P2 over Q2. Incidentally, this is a way that you can compute what the partial quotients are. If you know P0 over Q0 and P1 over Q1, construct these medians until you cross over x. The last time you could do so is the next partial quotient. But now we have P1 over Q1 and we have P2 over Q2, so we can start taking medians of them. Okay, we have not yet reached the next partial quotient, so we're on the same side of x as the lower index P1 over Q1. Again, again. Now if I tried to do it one more time, we would cross over the value of x. I apologize for the pen marks kind of crossing over here, but once we cross over the value of x, we're actually not going to consider that one anyway. We stop right here, and that's our value of A3, so this is our P3 over Q3. Okay, so suppose we have a infinite continued fraction expansion of an irrational number. For any n, we have the following inequalities. The distance from x to the convergent Pn over Qn is bigger than each of these things. An plus 2 over Qn plus 2, but it's also bigger than 1 over Qn times the quantity Qn plus 1. So let's look at the first one. Regardless of whether n is even or odd, Pn plus 2 is closer to x and on the same side as Pn over Qn was. In other words, it is in between Pn over Qn and Pn plus 2 over Qn plus 2. So the distance from x to the further away Pn over Qn is bigger than the distance from Pn plus 2 over Qn plus 2 to Pn over Qn. Multiplying all of this out, you're going to get that same balancing of p's and q's of consecutive index against each other in the numerator, which is a power of -1. And since we're in absolute value, I don't really care whether we're even or odd. You just end up with an plus 2 over qn plus 2. That's the first claim. The distance from x to Pn over Qn is bigger than the distance from Pn plus 2 over Qn plus 2 to Pn over Qn, which is exactly an plus 2 over Qn plus 2. The second claim, by the way, is proved very similarly. Regardless of how big an plus 2 is, if you construct one single mediant, you will be on the same side as the lower index Pn over Qn, because the next partial quotient can't be smaller than 1. So doing one mediant has not yet crossed over. So the mediant Pn plus 1 plus Pn over Qn plus 1 plus Qn is always going to be on the same side of x as the lower indexed Pn over Qn, so it's in between them. So you do the same argument. The distance from x to Pn over Qn has to be bigger than the distance from that mediant to Pn over Qn. Now our numerator is flat out just plus or minus 1, and our denominator is Qn times Qn plus 1. So the same basic idea for both of these gets two very similar looking results. Pn over Qn is very close to x, but it's not that close. We can place lower bounds on this error. So let's actually talk a little bit about what we just proved. We proved both of these inequalities, and it's not all that common to prove the same looking thing twice. These are both lower bounds on the distance from x to Pn over Qn. Is one of them better than the other? In which case, why didn't we only prove that one? The first inequality is actually a better one. So if an plus 2 is bigger than or equal to 1, which is always true, you can multiply an plus 2 by Qn squared and multiply 1 by Qn squared, and then add the same thing to both sides, and this inequality will remain true. You can factor out some things on both sides of this inequality. Okay, and now we can perform a little bit of division once we observe that an plus 2, Qn plus 1 plus Qn is exactly Qn plus 2. Doing a little bit more arithmetic shows that an plus 2 over Qn plus 2 is always bigger than or equal to 1 over Qn times Qn plus 1. In other words, this error estimate, this error is bigger than this number, which is bigger than or equal to this one. So this error estimate is quite literally always stronger than the other one. However, that error estimate relies on knowing an plus 2 and computing the partial quotient Qn plus 2. This error estimate only relies on computing the value of Qn plus 1. So it involves a little bit less work to use this, and it's actually more commonly used, that estimate there. But if you ever are trying to establish a lower bound on an error, and this isn't quite cutting it, this estimate might be a little bit better and might actually get you the results you need, so it's good to know it. Okay, suppose we have an irrational number x. If we list out all of the convergents and the semi-convergents in order of increasing denominator. So we start with p0 over q0. The denominator q1 is bigger, but now I am adding the positive q0 to make these mediants. Okay, and I keep adding q1 over and over again. So these are all getting bigger, but now I've reached p2 over q2. Adding q1 will be bigger. Now adding q2 over and over will keep making the denominators bigger. So we're listing out all of the convergents and semi-convergents, but specifically in order of the denominator getting bigger. Okay, here's our main result. For any positive integer n other than 1, the two rational numbers that are closest to x one of them being closest to x while bigger than it, and the other being closest while smaller, which is slightly different than saying the two rational numbers closest to x. Specifically, the one rational number closest and bigger and the one rational number closest and smaller. The way you find them is to look in this list, find the last term you can, so that the smaller index being used is odd, and find the last term you can where the smaller index being used is even. Restricting ourselves, by the way, to n not equaling 1 removes the possibility that n could possibly equal 2 denominators when q0 and q1 are both equal to 1. That can happen when a1 equals 1, and it's a common little exclusion from these theorems. We've seen it before, in fact. If you really wanted, you could consider as a special case what about n equals 1, but I don't actually care to do that. Before we begin the proof, though, let's discuss what this means. The semi-convergents, as they get closer and closer to x from one side or the other, until you have constructed a semi-convergent that's actually the next convergent, and now you start doing it from the other side, what you're always doing are looking at the closest rational number whose denominator is up to and including that value from one side or the other. So previously, we used this animation, I'm going to use the same one, to illustrate how semi-convergents approach x. Now we're going to use the same animation to claim that these semi-convergents are the closest rational numbers with denominator up to that large, at least from whatever side they are approaching. So we had our x, we had our p0 over q0, and our p1 over q1. Now I'm going to start listing semi-convergents with increasing denominator. If I stopped here, the closest rational number that is got denominator up to and including q1 and is bigger than x is this convergent. And the rational number up to and including denominator q1 but less than x, the closest one, is this convergent over here. However, if I allow my denominators to go up to q1 plus q0, I now have a rational number that's closer on the left. It's not actually closer than this convergent was. But if I'm specifically saying I'm looking for the rational number closest and above, and also the rational number closest and below, I've got this convergent and this semi-convergent. Now I've made, as long as I'm allowing the denominator to get a little bit bigger, a rational number that's even closer on the left. And if I let my denominator get bigger, I can find a closer one. And if I let my denominator get bigger, I can find a closer one. But now, this would violate the list of convergents and semi-convergents. This denominator is really too big. Okay. Stopping here, I now have a rational number of denominator up to and including q2 that's very, very close to x on the left. The next rational number I'll see that is closer on the right than p1 over q1 was actually q2 plus q1. The next one I would see would actually be 2q2 plus q1. That would be the denominator. And similarly, the next rational number I might see closer to x on the right would be 3p2 plus p1 over 3q2 plus q1, as long as I'm allowing denominators up to and including that value there. If I went a bit too far, I'd be on the wrong side of x, and we don't include that. Instead, we say this is p3 over q3, and now you can start constructing semi-convergence from the other side. So as you go through this process, what you're always making is the next rational number of smallest denominator possible that is still closer to x on one particular side or the other. At least that's what the theorem claims. So before we prove that theorem, we're going to observe the following little lemma. Suppose a, b, c, d are integers, b and d are positive, and ad minus bc is 1. Then if I make the rational numbers c over d and a over b, the interval between them has no rational numbers in it whose denominator is less than whatever the larger of the two denominators b and d are. The proof is actually quite straightforward. Suppose you have a rational number x over y that is in between c over d and a over b. The fact that c over d, by the way, is to the left of a over b follows from the assumption that ad minus bc is 1. This tells us that a over b is bigger than c over d. Okay, so if x is in between the two, then x over y, I apologize. If x over y is in between the two, then x over y, its distance to c over d is smaller than the distance from a over b to c over d. However, the distance from a over b to c over d would be ad minus bc over bd, and we just assumed that that numerator is 1. So we compute that xd minus cy over dy is less than 1 over bd. We know that the denominators are all positive, so we can multiply without flipping any inequalities. So xd minus cy must be less than y over b. But everything involved here is an integer. And specifically, we know that xd minus cy is positive because we assumed that x over y was bigger than c over d. So on the left, we have a positive integer. So y over b has to be bigger than an integer. So y has to be larger than b so that this fraction y over b could be at least as large as 1. So y has to be larger than b, and you can do a similar argument using not the interval from x over y to c over d, but the interval from x over y to a over b, and you'll show that y has to be larger than d. So the denominator y on our arbitrary rational number belonging to this interval has to be larger than both d and b. And this was on the assumption that AD minus BC is 1. So now what we can do is we can prove our result that the list of convergents and semi-convergents always gives you the closest rational numbers on one side or the other to x. So what we need to point out is the following equality, that k pn plus 1 plus pn times qn plus 1 minus k qn plus 1 plus qn times pn plus 1 is 1 in absolute value. So it's either plus or minus 1. But this is actually quite easy to see. If you actually distribute this out, all of your terms with k in them will cancel out, and you're left with our standard inequality, pn qn plus 1 minus qn pn plus 1 is plus or minus 1. So since this is true, that would exactly tell me that the interval between this number and this one contains no rational numbers whose denominator is less than whichever one is bigger, and certainly this number right here has the bigger denominator. So provided that k was not quite up to the next partial quotient, the semi-convergent that you're looking at here and the proper convergent, pn plus 1 over qn plus 1, are on opposite sides of x. Therefore, any rational number whose denominator is not bigger than the denominator of that semi-convergent, k qn plus 1 plus qn, has to be outside the interval between the two. Okay, so you cannot have rational numbers with smaller denominator inside that interval. That's exactly what our previous lemma tells us. So what two rational numbers with denominator up to and including kqn plus 1 plus qn are closest to x on either side? Exactly the left and right endpoint of that interval, pn plus 1 over qn plus 1, and the semi-convergent kpn plus 1 plus pn over kqn plus 1 plus qn. So in other words, this list of constructing semi-convergents, because of the equality at top combined with the lemma from the previous slide, tells us that you cannot have rational numbers with smaller denominator in between the two. So no rational number with denominator smaller than the denominator of the semi-convergent that you're constructing could possibly be closer to x than either the previous convergent you had on that side or closer than the semi-convergent on the other. So knowing full well that this topic has already been dragged on for quite some amount of time, we can now state the main theorem, which will take a while to prove, that the best approximations of the first kind for the irrational x include the convergence, but they also include some of these semi-convergents. These are the semi-convergents between pn over qn and pn minus 1 over qn minus 1. And which ones do they include? When you choose the coefficient k to be bigger than half the next partial quotient, those will be best approximations of the first kind. If it's less than half the next partial quotient, it won't be. In the very special case where the next partial quotient is even and you might have been able to pick exactly half, we're not going to claim one way or the other quite yet. So the semi-convergents march towards x from the direction, from the side of the previous pn minus 1 over qn minus 1. But note that their denominators, kqn plus qn minus 1, are bigger than qn. So if those semi-convergents are further away from x than pn over qn, they're definitely not best approximations of the first kind. However, we have shown that the interval between this semi-convergent and pn over qn doesn't contain any rational numbers whose denominator is smaller than the larger denominator, that of the semi-convergent. So if this semi-convergent is closer to x than the previous convergent, it is a best approximation of the first kind. In other words, we're trying to classify the choices of k so that these semi-convergents are closer to x than Pn over Qn is. So now let's look at the quantity alpha Pn plus Pn minus 1 over alpha Qn plus Qn minus 1. If you imagine alpha being a real parameter, if alpha was 0, you'd have exactly Pn minus 1 over Qn minus 1. If alpha goes off towards infinity, you'd end up with Pn over Qn. And just by taking a derivative and computing a sign, you can show that this is either increasing or decreasing according to whether n is even or odd, but it just moves monotonically from the lower index partial convergent to the larger index convergent. Now, when k is equal to an plus 1, and when k is equal to an plus 1 plus 1, these produce medians on opposite sides of x. This is something we've already shown. If you pick k to be equal to the next partial quotient, you get the next convergent. That's on the same side as Pn minus 1 over Qn minus 1, but if you made it a bit too large, you would cross over the value of x. And since alpha being a real parameter, this slides from one convergent to the next, there's a choice of delta somewhere in between 0 and 1, so that if you had this plus delta, you would have exactly moved from on one side to the other, somewhere in between an plus 1 plus 0 and an plus 1 plus 1, somewhere in between you are exactly equal to x. So x is exactly equal to some choice of real number, delta, between 0 and 1, where this all works out. Now this isn't a semi-convergent because delta is not an integer, but it's, a semi-convergent-ish kind of thing. You can actually compute that whether n is even or odd, you can solve this for x. Solve this for delta, and delta is exactly Qn plus 1x minus Pn plus 1 over Qnx minus Pn, and depending on whether n is even or odd, one of the numerator and denominator is positive and the other is negative. All right, so here's the statement of our theorem. Now it amounts to showing that when k is the ceiling of half an plus 1 minus 1, that's too far away from x, whereas if k is the floor of half an plus 1, that is closer to x. This floor is just rounding down. We've called it the integer part of something before, and I've mentioned that this notation is a little more common. This notation where the bracket is on the top is the ceiling. That's rounding up. So if something is even, its floor and its ceiling are the same number. So here you would get n plus 1, and here you'd get n minus 1. Those will be consecutive integers, not including half of that partial quotient. Remember, if this next partial quotient is even, this specific choice, we're not making a claim about one way or the other, but we would be showing that this one, bigger than half, is closer to x than is the convergent Pn over Qn, whereas this choice of k is not. If an plus 1 is odd, well then, dividing by 2 gives us n plus a half, so the floor is just n, that's n plus 1. But the ceiling would be n plus 1, minus 1 is n. These are now consecutive integers on opposite sides of half the next partial quotient. So whether an plus 1 is even or odd, the floor of half the next partial quotient plus 1 and the ceiling of the next partial quotient over 2 minus 1 are really the two values we want to test. We want the first one to be a best approximation of the first kind, and the second one to not be. Now let's go ahead and assume n is odd, just for convenience, so we can write some inequalities in specific directions. What we really want to show is this. This choice of k, the ceiling minus 1, is further away from x than was Pn over Qn, whereas this choice of k, the floor of half the next partial quotient plus 1, will be closer to x than Pn over Qn was. And we don't need to write absolute values here. This was part of the benefit of assuming n was odd. Pn over Qn is bigger than x, but these semi-convergents are increasing, so x minus this is the proper way to do it, whereas here you would have x minus that. So now what we're going to do from this inequality is we're going to add x to everything. We're going to subtract Pn over Qn. That's going to give us a 0 right in the middle. And remember that x was equal to an plus 1 plus delta Pn plus Pn minus 1 over an plus 1 plus delta Qn plus Qn minus 1, where delta was this specific quantity. So after we do all of that, you'll obtain a pretty nasty looking thing. You'll obtain exactly this. But now all of these terms, we have some shared denominators, and they're all positive. The denominator of everything up here is positive. So if I multiply them through, we don't have to worry about the fractions. And the middle is still just going to be 0. Okay. If you multiply and give all of them a common denominator and then get rid of the positive denominator, some terms will cancel out. We're skipping over a bunch of algebra, but a bunch of terms will cancel, and then you can do some factoring, and what you'll end up with is that this desired inequality is exactly equivalent to this. Okay, one of the things we're going to use, by the way, is that this thing is a nice thing to factor out, because what we have here is a balancing of consecutive p's and q's against one another. Specifically, since n is odd, the way it's been written and factored out here is +1, so you can cancel it out, divide from every term without having to flip any inequalities, which would make it equivalent to just this. Now this is a little bit simpler. So we have a denominator qn, partial quotient plus something between 0 and 1, minus 2 times this ceiling -1 minus a previous denominator should be positive. Whereas if you start moving some terms around, we still have a minus qn here. We have a minus qn times this. There's a lot of similarities between the two sides here. Basically, the only thing that's changing, by the way, is that you have a ceiling -1 or a floor +1, and that should be the difference between being positive and negative. Okay, so this is the chain of inequalities we want to establish. Now, whether the next partial quotient an plus 1 happens to be even or odd, you can check that both of these quantities are always bigger than or equal to 1. It's sort of why they were written this way in the chain of inequalities rather than making them look more similar by factoring out some minus signs. So if an plus 1 is even, say 2 times capital N, then this is exactly n, and you'll end up with exactly a 2n, but that's an plus 1. Those will cancel, you'll get a 2 here. Similarly, here you'll get a 2n over 2. That's just going to give you an n, which rounds down to n. This is going to be exactly 2. But when an plus 1 is odd, both of these are exactly equal to 1. So in either case, they're both bigger than or equal to 1. And again, this is just some arithmetic that you can check. We're going to skip over it. So the left term, which includes an plus 1 minus 2 times that, is larger than if this was a 1 plus delta. So I have a qn times 1 plus delta minus qn minus 1. I want to show this is positive. Well, it's definitely bigger than this. And here I have a 1 plus delta. That's definitely bigger than a 1. And qn is definitely bigger than qn minus 1, so this is definitely positive. So overall, this quantity is definitely positive. Similarly, using this inequality here, since it's being subtracted, this is less than replacing this quantity with just a 1. Notice that this minus sign does distribute to this delta, so you end up with a negative qn minus 1 minus qn times a quantity here, and whatever delta is, it's between 0 and 1. So this is a negative and another negative. That's definitely negative. So the theorem is proved. Exactly this crossover of half the next partial quotient is the deciding factor of being a best approximation of the first kind or not. But we haven't addressed the case of when the next partial quotient is even, and we exactly pick that to be our choice of k. All right, let's go ahead and test. Suppose the next partial quotient is even, and we make a semi-convergent by using half of that partial quotient. Is this a best approximation of the first kind or not? What we have to do is compare the distance of that semi-convergent to x versus x to the previous convergent Pn over Qn. Let's go ahead and assume n is odd so that we can start dropping some absolute values. Specifically, if n is odd, this convergent is actually bigger than x, so we're going to reverse that here. However, these semi-convergents were increasing towards x, so x was bigger than this. So we can drop this absolute value for free. Here we just reverse the direction. What we want to check is this distance less than this distance or not? Now let's suppose n is even. We would just get the opposite. Okay? But observe, we're basically checking the same inequality. If n is even, I would just multiply this by -1, and we'd get a reversed inequality, but it would look exactly the same. So between n being odd or even, we're checking the same inequality. It's just in n equals odd, we want less than. That will tell me that the semi-convergent is a best approximation of the first kind, whereas for n even, we're going to want bigger than. So let's proceed with the case where n is odd, and the next partial quotient is even. So we need to determine if this semi-convergent is a best approximation of the first kind or not. We know this is in fact the inequality we want to check. So add x to both sides, subtract Pn over Qn so that we get a comparison to 0. Remember that x was an plus 1 plus delta-ish kind of semi-convergent, and now we've got a bunch of positive denominators we can multiply through, giving us this terrible mess. Okay, however, once you expand all it out, some stuff will start to simplify as we've done before. So here's what we want to check. We want this gigantic mess to be negative. That will tell me that the semi-convergent using half the next partial quotient is a best approximation of the first kind if this inequality is true, and this is for specifically when n is odd. After expanding and canceling and using the fact that because n is odd, the quantity pn qn minus 1 minus pn minus 1 qn is positive 1, a bunch of similar cancellation and factoring compared to the previous work will be done. This reduces spectacularly to just is delta qn less than qn minus 1. In other words, is delta less than qn minus 1 over qn. But observe, qn is an qn minus 1 plus qn minus 2. If I cancel out a qn minus 1 from numerator and denominator, we get this. But now we could say that qn minus 1 is an minus 1 qn minus 2 plus qn minus 3. Cancel the qn minus 2 and proceed, and you'll end up exactly with this. Is delta less than 1 over an plus 1 over an minus 1? What we have here are the partial quotients marching up towards the index where we're making our decision, but in the opposite order. Okay, so an starts off the continued fraction and we work our way down to a1. Okay. As a side lemma, before we proceed with our main theorem here, for an irrational x, I claim that delta, which we did define as this absolute value, is in fact equal to the continued fraction with no integer part, and whose partial quotients are exactly those of x, but cutting off everything through the n plus first index. So our original definition of delta, remember, was that an plus 1 plus delta times pn plus pn minus 1 over an plus 1 plus delta times qn plus qn minus 1 equals x. Now observe, we have an an plus 1 pn plus pn minus 1 and an an plus 1 qn plus qn minus 1. So this is in fact pn plus 1 plus delta pn over qn plus 1 plus delta qn. And that's equal to x. Now, if you solve that for delta, you'll get exactly this here. Okay, so our claim is that this is actually this continued fraction expansion. So let's let n equal 0. Our claim amounts to what happens when we have q1x minus p1 over q0x minus p0. Now q1 is a1, p1 is a0, a1 plus 1, q0 is 1, and p0 is a0. So it's just this expression here. But in the numerator, we can factor in a1 out of a couple of terms. Now I see a shared factor of x minus a0 between two terms here, so I split this apart as two separate fractions, and we just get a1 minus 1 over x minus a0. However, x had continued fraction expansion a0, a1, a2, and this was the integer part. So if I subtract that integer from x, I now have an integer part of 0. So x minus a0 is 1 over a1 plus 1 over a2 plus 1 over a3 and so forth. So 1 over that brings out this integer part of a1. So in other words, 1 over x minus a0 is a1 plus 1 over a2, etc. Now these a1s cancel. I have a negative this continued fraction, but I'm in absolute value, so I can ignore it. I just have the continued fraction starting at index a2 with no integer part. So proceeding with our inductive proof, let's suppose we have an index n where everything works out like we hope. Let's move on to the next one. Well, qn plus 1 is an plus 1 qn times x with an additional qn minus 1 times x. Similarly, we write pn plus 1 in terms of its recursive form, and we can do this factoring up here in the numerator. But now we've got this shared factor of qnx minus pn. So split this apart into two terms. So here they cancel and we get the integer an plus 1. Here we've got the smaller index over the larger index, which I'm going to write as 1 over the larger index over the smaller index. This almost looks like our inductive assumption, except there's an absolute value. But whether n is even or odd, one of these is positive and one of them is negative. In other words, this is definitely a negative number. So I'm going to write it as minus its absolute value. And now I can make my inductive assumption that this absolute value is this continued fraction, but this is 1 over it. Okay, notice there's no integer part here, so this is 1 over an plus 1 over an plus 2, etc. So when you take 1 over that, the an plus 1s cancel out, and you're left exactly with a minus sign that gets ignored because of our absolute value, the continued fraction starting at index n plus 2 and proceeding from there. So we've inductively proved that delta can always be written like this, the continued fraction expansion of x having cut off all indices through index n plus 1. So with that little lemma proved, what were we doing? We assumed n was odd. This was really just so we could put inequalities in a particular direction. It wasn't that important of an assumption, but we'll see what it causes in a minute. The big assumption is that the next partial quotient is even, and we're looking at the semi-convergent constructed with exactly half that next partial quotient. Under the assumption that n was odd with a particular direction of our inequalities, it will be a best approximation of the first kind if and only if delta was less than this interesting continued fraction, which is a rational number. It is a finite continued fraction, but it uses the partial quotients of x up to the nth one, but in the reverse order. What happens when n is even? All of our starting inequalities will end up reversed. We made that comment a while back. But at one point, we did in fact divide out by pn qn minus 1 minus pn minus 1 qn. When n was odd, this was dividing by 1 and it did nothing. But when n is even, we'll be dividing by minus 1. So when we cancel it out from our inequality, we'll reverse the inequality back to the same direction as in the case when n was odd. So whether n is even or odd, it doesn't actually matter. If the next partial quotient is even, the semi-convergent above, using half the next partial quotient, is a best approximation of the first kind if and only if delta is less than this continued fraction. But what's delta? Our little lemma tells us that it's this continued fraction. So this is an irrational number. This is a rational number, and we're checking, does this inequality hold? If it does, then this semi-convergent is a best approximation of the first kind, and if it doesn't, then it's not. You can add the integer to both sides of this inequality. Both of these continued fractions have no integer part, but if you add the integer an plus 1, you get a slightly more pleasant to look at, symmetric looking form that both start with index n plus 1. Here you start with index n plus 1 as your integer part, and then you increase, making an irrational number. Here you start with that integer part and decrease, but terminating at a1, constructing some sort of rational number. The way you would check this inequality is to find the first partial quotient where the two sides are different. The first partial quotient where they're different, one of them's bigger than another. If you have a bigger partial quotient in an even index, that means the number is bigger, and if you have it in an odd index, that means the number is smaller. So this will hold exactly when the first index at which these two things are different has this side having a larger number in an even index, or this side having a larger number in an odd index. All right, 48 minutes in, where are we? Convergents are exceptionally good approximations to our irrational number x. Pn over Qn, the convergent, is the closest rational number to x of all the rational numbers with denominator up to that value. That just says they're best approximations of the first kind. But the distance from x to the convergent Pn over Qn is smaller than 1 over Qn times Qn plus 1. Observe that when the next partial quotient an plus 1 is bigger and bigger, that denominator is smaller and smaller, even compared to 1 over Qn squared. But an plus 1 isn't actually used in computing this convergent, meaning an plus 1 being very big does not make this denominator big, but it does make this error control very, very small. What that says is if you want to estimate x with a rational number whose denominator isn't that big, but is very, very close to x, what you're really looking to do is compute a Pn over Qn that stops right before a very large partial quotient. So if you see a very large partial quotient in the expansion for a number, stop your computation of convergence just before using it, and you'll have a rational number whose denominator isn't too big, because you did not use the very large partial quotient, but the distance to x is very, very small because the next denominator, which does use that large partial quotient, would show up there in the denominator. Convergents also happen to be the best approximations of the second kind. If you're looking for multiples of x that are close to integers, they're exactly what you're looking to do, the convergents. Semi-convergents are good approximations to x, just not quite as good as the convergents. If you're interested in the best rational approximations up to a given denominator and you want to know which one is bigger than x and closest and which one is less than x and closest, the list of convergents and semi-convergents tells you how to find it. Best approximations of the first kind is a little subtler. It's asking for which rational numbers are closest to x up to that size of denominator without paying attention to whether it was on one side or the other. It's a slightly trickier problem. The convergents are best approximations of the first kind and some of the semi-convergents, those made with more than half of the next partial quotient. If exactly half of the next partial quotient was an option, you check a certain inequality involving this nice symmetric expansion of the partial quotients of x around that particular index that you divided by 2. So let's do some examples. Let x be 1 and then 2, 2, 2, 2, 2, 2, 2. Compute the value of x. Of all the rational numbers whose denominator is less than 1,000, find the one closest to x on either side. So find the rational number with denominator less than 1,000, which is closest and bigger, and which one is closest and smaller. So observe if I were to add 1 to x, I would add 1 to the integer part, I would just get the expansion of all 2's. Meaning x plus 1 satisfies this nice expression that x plus 1 is 2 plus 1 over itself. Multiplying by x plus 1 gives us that since x is positive, x is the square root of 2. You can just double check this algebra if you're interested. So as a little side remark, we've computed the continued fraction expansion for the square root of 2. It's a 1 and then it's all 2's. Note that this continued fraction expansion doesn't terminate. So if you're interested in a quick little giggle, we've done through the whole course of the last several videos a very long proof that the square root of 2 is irrational. But let's continue with finding good approximations like the problem is asking. So what we want to do are compute convergence and semi-convergence. And since AI is equal to 2, there's not that many semi-convergents to compute. And in fact, we can stop our work once we reach denominators larger than 1,000. It's actually going to be faster just to compute the convergence and then backfill a few semi-convergents as necessary to get close to that value of 1,000 without going through all of them along the way. So we begin with our defined starting values. P0 over Q0 is A0 over 1, which in this case is 1. It's not the best approximation to root 2. P1 over Q1 works out to be 3 over 2. It's a bit better of an approximation to the square root of 2. Now we start computing recursively. Observe that since we've already used A0, all of the other partial quotients are 2. So we just keep doing 2 times the previous numerator plus the one before it, 2 times the previous denominator plus the one before that. You can check the computations here, 7 fifths, 17 twelfths, 41 over 29, 99 over 70. If we keep going, 239 over 169, 577 over 408, and 1393 over 985. Okay, the next convergent will definitely have a denominator bigger than 1,000, so I don't want to include it. So the previous few convergents before we hit this cutoff were index 6, 7, and 8, giving us convergence of 239 over 169, 577 over 408, and 1393 over 985 respectively. The next convergent is definitely not going to be considered because we were stopping once we hit a denominator of 1,000. But the semi-convergent involving Q7 plus Q8 will also definitely be bigger than 1,000. So if we start listing all of our convergents and semi-convergents, but ignoring the ones whose denominator are bigger than 1,000, it ends here. Okay, so we'll have P6 over Q6. Then we'll do that semi-convergent with P5 over Q5. But if I did it twice, because all of the partial quotients are 2, we would just have reached P7 over Q7. Then I'll do the semi-convergent of this with P6 over Q6. If I do it twice, I'll just be at P8 over Q8. And the next semi-convergent will be too big in its denominator, and that's where we'll stop. So here's the end of our list, cutting it off where the denominator becomes larger than 1,000. The ones that are less than root 2, those would be convergence with even index or semi-convergence that the smaller index term is even. So it's P6 over Q6 or P7 plus P6 over Q7 plus Q6 or P8 over Q8. And the ones which are bigger will be the convergence of odd index or the semi-convergence whose smaller index is odd. And that's P6 plus P5 over Q6 plus Q5, and P7 over Q7. Within each list, by the way, we are successively getting closer and closer to root 2. So of all the ones that are less than root 2, the closest one is the last element in that list, and of all the ones that are more than root 2, the closest one is the last element in that list, which happen to both be actual convergents, P7 over Q7 and P8 over Q8. All right, so we found that P8 over Q8 is a pretty good approximation, 1393 over 985. Note, by the way, that the distance from the square root of 2 to P8 over Q8 will be less than 1 over Q8 times Q9. If you compute Q9, it's 2,378. So this rational number, 1393 over 985, is very close to root 2. Its distance to root 2 is less than 1 over its denominator times the next denominator, which turns out to be less than 1 over 2 million. So this approximation, which has a denominator roughly on the order of 1,000, is within less than half a millionth of the desired value. In fact, using a computer, it's very, very close. It's about 1/3 of a millionth away. If you wanted to get the same quality of approximation with a decimal, if you want to be within a millionth, you need 7 decimal points. Okay, that's a rational number whose denominator is very, very big. So continued fractions give us rational numbers that are much better approximations than just taking more and more decimal points. And I don't mean better in that they're closer to x. You could always take more decimal points to get as close as you want, of course, but you get really close without having to worry about extremely large denominators. This is the power of continued fraction convergence. So let's take a look at another example. Just take as a given that the continued fraction for pi begins in the following way. Its integer part is 3, pi is bigger than 3, and then it's 7, 15, 1, 292, followed by several 1s and a 2, and so forth. So we are asked to identify 2, quote, unreasonably good, end quote, rational approximations to pi, and estimate the errors in these approximations. So remember that extremely good approximations, in other words, they're very, very close even compared to the size of the denominator, are found by computing convergence that stop right before using large partial quotients. So the 2 largest partial quotients we see are 15, that's actually pretty big for a partial quotient, and 292 is quite enormous. You don't see partial quotients that big very often. So the estimates that stop right before the second index and right before the fourth index will be very good approximations. So we're going to compute through index 5 just so that we can do some estimates along the way. P0 over Q0 all the way through P5 over Q5, you can compute them, you can verify. Here they are. So let's use the estimate that the distance from x to its nth convergent is less than 1 over Qn times Qn plus 1, but it's bigger than an plus 2 over Qn times Qn plus 2. So for n equals 1 and n equals 3, what do we get here? The distance from pi to 22 over 7 is somewhere in between 1 over 7 times 113 and 1 over 7 times 106. But the distance from pi to 355 over 113 is somewhere between these 2 rational numbers. Observe that this is a very tight error estimate. The difference between the 2 sides is actually a fairly small number. So we actually know pi to a pretty high degree of accuracy using these rational numbers 22 over 7 and 355 over 113. 22 over 7 is a classically known very good approximation to pi. 355 over 113 has also been known for quite a long time as well. Incidentally, 22 over 7 is good to about 2 decimal places for pi, but 355 over 113 is good to about 6 decimal points. Even though the denominator is only a 3-digit number, it's good as an approximation to 6 decimal points. And you can check, by the way, that 113 pi, if you plug that into a calculator, it is really, really close to an integer, especially when you consider that you only multiplied by a fairly small 113. So we're about to cross the hour mark. Let's just do one final thing. Again, with continued fraction for pi being what it is, find the rational number whose denominator is as small as possible, but it has to be a better approximation to pi than 355 over 113. In other words, we want to find a better approximation than 355 over 113. What is the simplest fraction, the one with smallest denominator, that we could possibly use? In other words, we're looking for a best approximation of the first kind, but the first one, if we were to list them in order of increasing denominator, the first one that appears after P3 over Q3. So it will be a semi-convergent of the form kp3 plus p2 over kq3 plus q2, where that k is bigger than or possibly equal to half the next partial quotient, which is 146. But when the next partial quotient is even, 292, this is the tricky case. So maybe for 146, that will be a best approximation of the first kind. However, for 147, it definitely will be. So our answer might be using 146 as k, or it might be using 147 as k. So one of these two rational numbers is the correct answer. Now we can actually check whether this semi-convergent is a best approximation of the first kind by comparing, starting with this cutoff index as your integer part and proceeding after that point and getting this irrational number. Is this less or is it not less than starting with this as your cutoff point and working backwards, 1, 15, 7, 3. So observe that these are the same. These are the same. And now I have a difference. Okay, this is the first time these two numbers have different partial quotients, a 1 versus a 15. Well, 15 is definitely bigger. What index is it appearing in? It's appearing in index 1, 2. In the second index, which is even, a larger number makes you bigger. So this number is bigger than that one, meaning that this choice of semi-convergent really is a best approximation of the first kind. So our actual solution is this rational number. What does this mean? 355 over 113 is really close to pi. I'd like to do better, but I'd like to use a rational number. If you want to use a rational number and approximate pi closer than this, you need a denominator at least as large as 16,604. This is the next rational number in terms of size of denominator that's closer to pi than this one. This is just to stress that this convergent is unreasonably close to pi.